So this is the launcher we used in our Ballistic Pendulum project. It consists of 3D printed parts. There's a launching pad that's connected to this rod, and in between them there's a spring, so when you pull it back and release, the launching pad moves forward. This is our projectile. It's a black ball. If we put it in, we can pull back, and it gets launched out. This is our pendulum. It consists of a tape arm connected to another 3D printed box, which fits the ball. It has like some tape in there so that it sticks on impact. Tape on the outside so that it's black and it contrasts against a white background, which is what we used in the video. Here's the arm that holds up the pendulum. It's also 3D printed and taped down to the desk.
Doing the Ballistic Pendulum project. That's Abhishek, that's Ayush, and I'm Anna.
All right.
The velocities were found by uploading a video of the collision into Tracker and using a metal ruler to set the calibration stick to a perfect 1/10 of a meter. This method was also used to find the height of the pendulum after the collision at its highest point. We found our masses by using a metal scale to find the mass in grams and then converting the masses to kilograms.
To calculate the momentum before and after collision, the equation momentum equals mass times velocity and conservation of momentum statements were used. When substituting in values, we account for the fact that the pendulum starts at rest and the velocity of the ball and the pendulum will be the same after collision due to the fact that a perfectly inelastic collision requires the ball and pendulum to travel together. The change in momentum was calculated to be negative 0.0121 kilogram meters per second and have a negative 12.3% change. Change could be accounted for by the fact that the pendulum veered slightly upon impact in a direction Tracker is unable to account for.
The change in energy was found by subtracting the total energy at the top of the swing from the total energy at the moment after the collision. In the initial scenario, the pendulum is at what we consider zero height, so the potential energy was zero. In the final scenario, the pendulum stops moving, so the velocity and subsequently kinetic energy is zero. By subbing in values and subtracting as shown, the change in energy can be found to be negative 0.0408 joules. Using the percent change formula that was previously defined, the percent change can be found to be negative 61.1%. For these calculations, we worked with the assumption that this scenario only had conservative forces, but due to outside forces such as air friction, some of the total energy of the system was converted to heat and sound, causing the loss in energy. In order to calculate the kinetic energy lost during the collision, the kinetic energy of the ball and the pendulum in the instant after the collision was subtracted from the kinetic energy of each object before the collision. In the instant before the collision, the pendulum is at rest, making its kinetic energy zero. After the collision, the objects travel together, making their velocities equal. Values from the data table can be substituted in to find that the change in kinetic energy is negative 0.0644 joules. And using the percent change formula, the percent change is negative 49.1%.
While the momentum was relatively preserved and kinetic energy was lost upon collision, the energy of the pendulum decreased rather than remaining the same. We learned that outside variables in the real world, such as air resistance and a slight twist in the pendulum, will prevent the ideal experiment from occurring.